Web Assign 11, Question 3, Part C. Once again, we're asked to determine what's oxidized and what's reduced. And in order to do that, we've got to assign oxidation states for each element within each species in this equation. Let's start with silicon tetrachloride. Between silicon and chlorine, the more electronegative atom is chlorine. Fonkel are the four most electronegative elements, and chlorine is in that. That means chlorine will take its normal charge based on position in the periodic table. Silicon would take whatever charge is needed in order to make the sum of the oxidation states equal to the overall charge for the compound, which, since nothing is written to the upper right of the symbols, is 0. You might be able to do this math in your head, but I'll show work anyway. One atom of silicon whose oxidation state is unknown, when added together with 4 atoms of chlorine whose oxidation state is known to be -1, should equal the overall charge for the compound of 0. We'll add 4 to both sides, and x works out to be +4. So that means that silicon's oxidation state within silicon tetrachloride is a +4. Next compound, water. Between hydrogen and oxygen, the more electronegative atom, of course, is the oxygen. Oxygen takes its normal charge based on position in the periodic table. Hydrogen, the less electronegative atom, will take whatever charge is needed so that the overall charge of the compound is met when the sum of the oxidation states are added together. So in this compound we have 2 atoms of hydrogen of initially unknown oxidation states. 1 atom of oxygen whose oxidation state is known to be -2, and an overall charge of 0. We'll simplify a little bit, add 2 to both sides, and divide by 2, and we get x equal to 1. So we know that hydrogen's oxidation state within water is a +1. Next compound to consider, hydrochloric acid. Between hydrogen and chlorine, of course, chlorine is the more electronegative atom, Fonkel. And for this one, I think you can see it. You have 1 atom that's -1, and 1 atom that's got to be something else so that when the oxidation states are added together, the overall charge is met, and the overall charge is 0. So hydrogen's got to be a +1 to cancel out the -1 of chlorine. SiO2. Between silicon and oxygen, the more electronegative atom, of course, is oxygen. So oxygen takes its normal charge based on position in the periodic table. Silicon will take whatever charge is needed so that when the oxidation states are added together, it matches the overall charge of the compound, which, since nothing is written to the upper right of the chemical symbols, is 0. We'll simplify a little bit, add 4 to both sides, and we see that x equals 4. That means that silicon's oxidation state within silicon dioxide is a +4. Let's list all of those findings. So we've worked out oxidation states for each element within each chemical species in this equation. Okay, whose oxidation state changed in going from the left side of the equation to the right side of the equation, if any? First, let's look at silicon. It's +4 within silicon dioxide, or tetrachloride, and it's +4 within silicon dioxide. There's no change, and therefore silicon was neither oxidized nor reduced. Chlorine, -1 within silicon tetrachloride, also -1 within hydrochloric acid. No change, and therefore chlorine was not oxidized nor reduced. Hydrogen, within water, it's +1, and within hydrochloric acid, it's still +1. No change. Therefore, hydrogen was not oxidized nor reduced. Lastly, oxygen, within water, it's -2. Within silicon dioxide, it's also -2. That means there was no change, and therefore oxygen was neither oxidized nor reduced. If no element that appears in the equation experiences either an increase or a decrease in oxidation state, then it's not an oxidation-reduction reaction. And WebAssign wants you to write the word none, N-O-N-E, in each of the boxes below the equation.